For other types of graphs, you may see origin symmetry, and you can recognize that when you actually look at a picture of one. You'll see that, for example, opposite quadrants, like quadrant 1 here and quadrant 3, will have a similar picture in it, or quadrant 2 and quadrant 4 will look the same. And the other way that you can tell is when you input opposite values of x, the output now will be opposite values of y, and you can see that with the coordinates that I have on these two graphs here. The input is plus and minus 2, but the output is plus or minus 8, which is a little different than what we saw with y-axis symmetry. When we input opposite values of x, we saw the same y value out for y-axis symmetry. Let me give you an example of origin symmetry. And we're showing you this function, y equals x cubed over x squared minus 1. Now you could graph it, and let me see if I can pull up the graph here of this one. This is what this one would look like. Now if you're going to input the graph, make sure you put parentheses around the numerator and parentheses around the denominator, otherwise it's going to do the division at the wrong time. So tell the calculator where the numerator is versus the denominator. But when you graph it, although it looks a little strange, all I need to see is that opposite quadrants have the same pictures in them. This one seems to have like a check mark, this one has a check mark down here, this one has a little blurb and a little blurb down there as well in opposite quadrants. Another way to do it without the graphing calculator is by looking at the numbers. Now this time I can't use positive 1 and negative 1 because that's going to make my denominator undefined. So I'm going to have to pick two other opposites. I pick 2 and negative 2, 3 and negative 3, as long as my denominator doesn't go undefined. And when I plug in the negative 2 and cube it, and then put in the negative 2 and square it, I'm going to end up with the number negative 8 over positive 3 when I simplify it. But when I put in the positive 2, you can see now the numerator is going to be a positive number, and the denominator is still going to be 3, which is showing me what this idea over here is about the input opposite x's, output opposite y's. And so if I were to plot those, I'd see that they lie in opposite quadrants, plot both of those points. Algebraically, the proof says if I let x equal negative x and y equal negative y, simplify it, and you will get a similar equation. From what you started with. Similar just means that you may need to multiply the left and the right side of the equation by negative 1 so that you see the exact same equation. So for example, in this problem, if I let negative y equal y, negative x equal x, so everywhere there's an x, it switches out to its opposite, and then simplify it. I'll just come over here with that. It becomes a negative y equals a negative to the third power is still going to be negative. X to the third is x to the third. And on the bottom, a negative x squared is going to be positive x squared minus 1. Now you can see this isn't exactly what I started with, but it's an equivalent equation. If I multiply both sides by the number negative 1, I'm going to get positive y equals. When you multiply the other side by negative 1, you only multiply the numerator by negative 1. So this becomes positive x cubed over x squared minus 1. And I'm back to the original.